Section: Introduction. In this section, we discuss how we're currently experiencing a significant shift in the way benchmarks are used in machine learning research. Datasets like ImageNet, MS-COCO, GLUE, and BigBench have played a crucial role in pushing the field forward by offering standardized scenarios for model comparison. However, as these benchmarks have been used extensively, they've started to show their limitations. Each time a model is tested, it potentially reveals information about the test data, gradually diminishing the benchmark's ability to measure how well a model can generalize to new data. This situation creates a dilemma where new methods must outperform highly optimized existing methods, often leading to models that are overfitted to these benchmarks. We propose a shift towards what we call lifelong benchmarks. The main aim of these benchmarks, especially in the context of visual tasks, is to evaluate how well models perform on data that closely represents the real world. For example, the CIFAR-10 benchmark was designed to test if classifiers could accurately distinguish between 10 different categories, such as dogs versus cats. Over time, to maintain the challenge and relevance of this benchmark, newer versions with more diverse and challenging samples were introduced. However, the effectiveness of these benchmarks has decreased due to overfitting at both the individual and community levels. To address this, we introduce two new benchmarks, Lifelong CIFAR-10 and Lifelong ImageNet. These benchmarks are designed to continuously expand, adding new test samples to prevent models from overfitting to a fixed dataset. One of the challenges with these expanding datasets is the increased cost of evaluation. For instance, evaluating our current models on Lifelong CIFAR-10 and Lifelong ImageNet requires significant computational resources. This issue is not unique to our benchmarks but is a common problem in evaluating large-scale models. As models and datasets grow, so does the cost of evaluation. We pose the question: is it possible to reduce these costs while still accurately assessing model performance? To tackle this, we draw inspiration from computerized adaptive testing, which is used in exams like the GRE and SAT. These tests don't require every question to be answered. Instead, they adaptively select a subset of questions based on the test taker's responses. This method efficiently assesses proficiency with fewer questions. Similarly, we aim to evaluate models on a subset of samples from our lifelong benchmarks. We introduce a method called sort and search, S&S, which dynamically selects test samples for evaluating new models based on their difficulty, significantly reducing the computational cost of evaluation. Our key contributions in this work include the introduction of the lifelong benchmarking framework, the creation of lifelong CIFAR-10 and lifelong ImageNet benchmarks, and the development of the sort and search method for efficient model evaluation. These contributions significantly reduce the computational costs of model evaluation while maintaining accuracy. For the curation of our lifelong benchmarks, we chose CIFAR-10 and ImageNet due to their popularity, the diversity of models trained on them, and the availability of numerous dataset variants. Our lifelong CIFAR-10 combines samples from 22 different domains, including synthetic distribution shifts and samples generated by diffusion models, resulting in a dataset of 1.69 million unique images. Similarly, Lifelong ImageNet includes samples from 43 unique domains, leading to a dataset of 1.98 million samples. These benchmarks are designed to increase sample diversity and better represent the visual world, making them more effective tools for evaluating model performance. Section Summary. In this section, we introduce the concept of lifelong benchmarks as a new framework for robust and efficient model evaluation in computer vision. We curate two lifelong benchmarks, Lifelong CIFAR-10 and Lifelong ImageNet, each containing millions of diverse samples to restore representativeness to visual world evaluations. We propose the sort and search method for efficient model evaluation, significantly reducing computation costs by over 99.9% on our lifelong benchmarks while accurately predicting sample-wise performance. Section: Lifelong Benchmarks, Formulation, Challenges and Approach. In this section, we delve into the concept of lifelong benchmarking, outlining its objectives and the significant challenges it presents. We start by defining what we mean by lifelong benchmarking. Imagine we have a set of examples, each consisting of a data sample and its corresponding label. These examples come from a specific distribution of tasks we're interested in. Alongside, we have a collection of models. Each model is designed to predict labels for data samples. In the context of lifelong benchmarking, we enhance this setup with three key operations: inserting new labeled examples, inserting new models, and evaluating the performance of each model on our task. One of the main hurdles we face is ensuring that both our collection of models and examples can grow over time without causing our system to overfit or become less useful to the research community. To keep our benchmarking efforts practical, we need a way to efficiently evaluate model performance every time we add new models or examples. The straightforward approach of re-evaluating every model with every example each time we add something new becomes impractical very quickly due to the sheer volume of computations required. To tackle this, we introduce two main strategies. First, we incorporate a prediction cache into our benchmarking framework. This cache stores the outcomes of model evaluations, allowing us to save on computation time by not repeatedly performing the same evaluations. Second, we devise methods to smartly update this cache with new predictions by carefully selecting a small subset of models or examples for evaluation, which helps us predict the rest of the cache entries accurately. Our approach also addresses the challenge of efficiently inserting new models and examples into our system. When new models are developed, instead of evaluating them on all existing examples, we select a small, representative subset of examples for evaluation. This helps us accurately estimate how these models would perform on the entire set of examples. Similarly, when we obtain new examples, we select a small subset of models to evaluate on these examples, which assists in accurately predicting how the rest of the models would perform on the new examples. While the idea of lifelong benchmarking has not been widely explored, the specific challenge of efficiently evaluating models has received more attention. Several methods have been proposed in related work, focusing on ranking models or efficiently evaluating them on unseen datasets. However, these methods generally predict dataset-level metrics rather than the instance-level metrics we require for our prediction cache. Some recent works propose efficient instance-level evaluations, but they face scalability issues with very large datasets, unlike our approach, which can handle significantly larger datasets efficiently. In summary, our approach to lifelong benchmarking is designed to be scalable and efficient, enabling the continuous expansion of model and example collections without becoming impractical. Through the use of a prediction cache and strategic sampling for cache updates, we can maintain an up-to-date evaluation of model performance, supporting the ongoing development and comparison of models in a way that is both practical and useful for the research community. Section Summary. In this section, we formalize the objective of lifelong benchmarking and outline the challenges it presents. We introduce the concept of a lifelong benchmark, which involves expanding both the model and sample collections over time. To address the challenge of efficiently computing metrics as new models or samples are inserted, we propose using an instance-level prediction cache and strategies for its efficient population through judicious sampling and inference. Our methodology, illustrated in Figure 2, allows for scalable evaluation on large test sets, unlike existing approaches with high memory and time complexities. Section: Efficient benchmarking with sort and search. In this section, we introduce an efficient evaluation framework for lifelong benchmarking, which we call Sort and Search, S&S. This framework is inspired by the computerized adaptive testing paradigm and consists of two main parts. Firstly, ranking test samples from the entire dataset pool based on their difficulty, which we refer to as sort, and secondly, selecting a subset from this pool to estimate performance, which we call search. Our goal is to address the two critical operations we previously identified with our framework. Let's start by explaining the setup. Imagine we have a pool of evaluations involving a certain number of models, let's say M models, tested on a certain number of samples, let's say N samples. For each model, we predict whether it correctly classifies each sample, resulting in a binary outcome, 1 for correct classification and 0 for incorrect. By compiling these predictions for all models across all samples, we create a binary matrix. This matrix has m rows, 1 for each model, and n columns, 1 for each sample. Our objective is to arrange the columns of this binary matrix in a way that ranks the samples from easiest to hardest. The easiest samples are those correctly classified by all models, all ones across a column, and the hardest are those incorrectly classified by all models, all zeros across a column. We aim to find the best possible arrangement, or permutation, of these columns. This optimal arrangement is represented by a special kind of binary matrix that, when applied to our original matrix, reorders the columns from easiest to hardest samples. To achieve this, we create a ranked accuracy prediction matrix. This matrix is similar to our original binary matrix but is adjusted row by row. For each row, we apply a threshold. Samples predicted correctly up to this threshold are considered easy, marked with 1s, and those predicted incorrectly beyond this threshold are considered hard, marked with 0s. The challenge is to order the samples in such a way that the difference between our original predictions and this ideal ranked matrix is minimized. Solving this problem involves finding the optimal permutation matrix, but we also need to determine the best way to adjust our ranked accuracy prediction matrix. We tackle this by alternating between optimizing the permutation matrix, keeping the ranked matrix constant, and then optimizing the ranked matrix, keeping the permutation constant. This approach is somewhat similar to an expectation maximization (M) algorithm, where we iteratively refine our solution until we find the best arrangement. In summary, our sort and search framework aims to efficiently benchmark models by sorting test samples based on difficulty and searching for the best subset to predict performance. Through this approach, we hope to streamline the evaluation process in lifelong benchmarking scenarios. Section Summary. In this section, we introduce an efficient evaluation framework called Sort and Search, S&S, inspired by computerized adaptive testing. S&S involves ranking test samples based on difficulty, sort, and sampling a subset for performance prediction, search, aiming to address key operations in lifelong benchmarking. The framework focuses on optimizing a global permutation matrix to rank samples from easy to hard, facilitating efficient prediction on new models. Section. In this section, we delve into the process of optimizing a given parameter. From our initial observation, we understand that the parameter in question is binary, which inherently makes the task of finding its optimal state a complex, NP-hard problem. To navigate this complexity, we explore ways to simplify the subproblem at hand. We start by introducing an algorithm designed to tackle scenarios where it's possible to arrange samples in a strictly decreasing order based on their difficulty. This difficulty is gauged by the number of models that correctly classified each sample. However, arranging samples in such a strictly decreasing manner is impractical in real-world scenarios. To address this, we propose an alternative approach that calculates soft confidences, thereby allowing us to maintain the strictly decreasing order constraint. Additionally, we examine a third alternative algorithm that does away with the need for a strictly decreasing order altogether. Focusing on the first approach, dubbed sorting by sum, we explain how to sequence samples if they can be arranged in a strictly decreasing order of difficulty. Essentially, the difficulty of a sample is inversely related to the number of times it was correctly classified by the models, meaning more correct classifications indicate an easier sample. By employing a straightforward algorithm, we can sort samples from easiest to hardest based on the sum vector across rows for each column. This method, while intuitive, faces practical limitations due to the unrealistic assumption of a strictly decreasing order of difficulty, especially when the number of samples significantly exceeds the number of models. To circumvent this limitation, our second method, sorting by confidence sum, modifies the constraints on the samples, allowing for a range of confidence values rather than binary ones. This adjustment enables a unique ranking of all examples, making the sorting by sum method viable and potentially more efficient in ranking samples. Our third strategy, recursive sorting by sum, further relaxes the assumption of equal difficulty among samples. When faced with samples of equal difficulty, we propose an iterative solution that alternates between optimizing the given parameter while keeping another parameter constant, and vice versa, through a dynamic programming search algorithm. This recursive approach involves dividing the vector into subsets of samples with equal sums and reordering them based on specific thresholds. This method not only refines the solution with each recursion but also breaks ties by favoring the model that minimizes error most effectively. Through these strategies, we aim to simplify the optimization process of the given binary parameter, acknowledging the inherent challenges and proposing practical solutions to overcome them. Section Summary. In this section, we explore methods to optimize the binary matrix P, given its binary nature, which poses a nitrogen monophosphide hard problem. We introduce algorithms like sorting by sum and sorting by confidence sum to simplify the subproblem by ordering samples based on difficulty levels, either by the number of models classifying them correctly or by considering confidence values. Additionally, recursive sorting by sum is proposed to handle cases where samples have equal difficulty levels, iteratively optimizing P and Y to improve the ordering. Section. Here, we discuss how to optimize the prediction matrix B group color, black, $Y, $E group. We reiterate that we want to find a row-wise threshold B group color, black, $K, $E group, minimizing the error with the matrix B group color, black, $AP, $E group for a given permutation B group color, black, $P, $E group. To optimize B group color, black, $Y, $E group given a B group color, black, $P, $E group, we propose an algorithm based on dynamic programming, called DP search, which operates row-wise on each row B group color, black, $Y, underscore I $E group, detailed in listing 2, DP underscore search. Given a row, it computes the difference between number of B group color, black, $1 E groups and number of zeros for each index based on a prefix sum structure. Due to the prefix sum structure, for an input of size B group color, black, $N E group, the dynamic programming approach reduces the time complexity from quadratic B group color, black, $O, N squared $E group, to linear B group color, black, $O, N $E group. The optimal threshold B group color, black, $K $E group is the maximum value in this vector. The vector B group color, black, $Y, underscore I $E group is simply B group color, black, $1, underscore K caret top, 0, underscore NK, caret top, $E group where B group color, black, $1, underscore K $E group is a vector of all ones of size B group color, black, $K $E group and B group color, black, 0, underscore NK, $E group is a zero vector of size B group color, black, $NK $E group. DP search is guaranteed to return the globally optimal solution, defined as Theorem 5.1 optimality of $Y, given $P, For any given $A, underscore I in 0, 1, caret 1 times n, and $P, the DP search algorithm returns an ordered prediction vector $Y, underscore I in 0, 1, caret 1 times n, which is a global minimum of $vert A, underscore I, P, Y, underscore I vert underscore $1. The DP search algorithm when applied row-wise independently returns the optimal B group color, black, $Y, $E group given B group color, black, $P, $E group. Now, having optimized the ranking problem, we have a permutation B group color, black, $P, caret asterisk $E group from the data matrix indicating the order of the samples based on difficulty. In the next section we use B group color, black, $P, caret asterisk $E group towards either evaluating new models or adding new samples efficiently. In this section, we delve into the process of optimizing the prediction matrix, which we denote as Y. We emphasize our objective to identify a row-wise threshold, referred to as K, that minimizes the discrepancy with the matrix AP for a specific permutation P. To achieve this, we introduce an algorithm based on dynamic programming, named DP search, which tackles the optimization on a row-by-row basis. For each row, the algorithm calculates the difference between the number of ones and zeros at each index, utilizing a prefix sum structure. This structure allows us to reduce the computational complexity from quadratic, which is proportional to the square of the input size, to linear, directly proportional to the input size. The optimal threshold, K, is identified as the maximum value within this calculation. The resulting vector for each row is constructed as a sequence of K1s followed by nk zeros. We guarantee that DP search will always find the globally optimal solution. Upon optimizing the prediction matrix Y with respect to a given permutation P, we obtain a new permutation, denoted as P*, which reflects the order of samples based on their difficulty. Moving forward, we use P to either evaluate new models or incorporate new samples more efficiently. When it comes to efficiently selecting by search, given our optimal permutation P*, we assume this order of sample difficulty can be generalized to new models. Since the challenge can be addressed separately for each model, our aim is to predict the accuracy for each of the n samples across all new models. The main hurdle is to accomplish this by evaluating only a small subset of samples for each model. To tackle this, we first clarify that the constraints on Y imply a thresholding operation for every model independently. Focusing on optimizing for the first new model, we split the task into two parts: selection and optimization. The selection involves choosing the best subset of observations to sample from. A straightforward approach is to sample points uniformly across the range, aiming to minimize the discrepancy between the actual threshold and one predicted from our sampled points. We also explore how this method compares to random sampling. For the optimization part, given our selected observations, we use the DP search algorithm to determine the threshold, which is then extrapolated to the full set of samples to generate the prediction vector. This vector is similarly constructed as a sequence of ones followed by zeros, based on the determined threshold. Evaluating the quality of our predictions involves calculating the mean absolute error, MA, between the predicted and actual values, using the Hamming distance. However, we also consider the agreement between predictions and actual values that could occur by chance. To account for this, we use a normalized measure known as Cohen's kappa, which adjusts for chance agreement. This measure helps us understand the true accuracy of our predictions beyond what might be expected randomly. In summary, our approach not only allows for the efficient evaluation of new models but also sets the stage for incorporating new samples into the benchmark with minimal effort. Section Summary. In this section, we optimize the prediction matrix Y, given a permutation P, using the DP search algorithm, which reduces time complexity from quadratic to linear. The algorithm guarantees the globally optimal solution for finding the threshold minimizing error with the matrix AP for a given permutation P. We then focus on efficiently selecting and evaluating new models based on the optimized permutation matrix P***, aiming to predict accuracy across all samples per model while evaluating on a subset of samples. Section. To add new samples into our lifelong benchmark efficiently, we have to estimate their difficulty with respect to the other samples in the benchmark. To efficiently determine difficulty by only evaluating B group color, black, $M, LLM, $E group models, a ranking over models is required to enable optimally subsampling a subset of B group color, black, $M, $E group models. This problem is quite similar in structure to the previously discussed addition of new models, where we had to evaluate using a subset of B group color, black, and LLN, E group samples. How do we connect the two problems? We recast the same optimization objectives as described in EC 1, but replace B group color, black, $A, $E group with B group color black, $A, caret top $E group and B group color black, $Y, $E group with B group color black, $Y, caret top $E group. In this case, EQ1 would have B group color black, $A, caret top P, $E group, which would sort models, instead of samples, based on their aggregate sum over samples, i.e. accuracy. Optimized using algorithm, baseline equals char. Base. Shape equals circle. Fill equals climb blue 2. Draw equals white. Thick. Drop shadow equals shadow x shift equals 0.2x. Shadow y shift equals minus 0.2x. Intercept equals 1 pt, char. 1. To obtain B group color, black, $P, caret asterisk $E group. Ordering the models from classifying least samples correctly to most samples correctly. Here, algorithm, baseline equals char. Base. Shape equals circle. Fill equals climb blue 2. Draw equals white. Thick. Drop shadow equals shadow x shift equals 0.2x. Shadow y shift equals minus 0.2x. Intercept equals 1 pt, char. 1. Is sufficient, without needing to solve the joint optimization. Baseline equals char. Base. Shape equals circle. Fill equals climb blue 2. Draw equals white. Thick. Drop shadow equals shadow x shift equals 0.2x. Shadow y shift equals minus 0.2x. Intercept equals 1 pt, char. 3 winking face. Because accuracies, sum across rows, are unique as the number of samples is typically much larger than the number of models. In case of new incoming samples B group color, black, $delta N $E group, we similarly would treat every sample independently and optimize the predicted array B group color, black, $Y, caret top underscore N plus 1, $E group using efficient selection by search. Efficient selection by search. In this section, we discuss how to efficiently incorporate new samples into our ongoing benchmark by determining their relative difficulty. To do this without having to evaluate them against all models, we only assess them using a smaller, optimally chosen subset of models. This approach is quite similar to how we previously added new models by evaluating them with a subset of samples. The connection between these two scenarios is established by adapting the optimization objectives we used before. Instead of arranging samples, we now arrange models based on their overall performance, specifically their accuracy across samples. This is achieved using a specific algorithm that orders models from those that classify the fewest samples correctly to those that classify the most correctly. This algorithm is particularly effective because the number of samples usually far exceeds the number of models, making each model's accuracy unique. When it comes to adding new samples, we treat each one independently and optimize its predicted outcomes using a method called efficient selection by search. To empirically validate our framework, we conduct experiments focusing on two main tasks: efficiently estimating the difficulty of new samples and efficiently evaluating the performance of new models. We delve into various design choices within our sort and search framework through these experiments. For our experiments, we use a large number of pre-trained models from the CIFAR10 and ImageNet datasets. Specifically, we use 31,250 CIFAR10 models and 167 ImageNet models. When adding new samples to the CIFAR10 benchmark, we set aside around 500,000 samples for evaluation and use approximately 1.2 million samples for sorting. This is not necessary for ImageNet due to the smaller number of models, making direct evaluation more feasible. For evaluating new models in the CIFAR10 benchmark, we divide the models into two groups, a smaller subset for sorting and the rest for evaluation. Similarly, for ImageNet, we select a small subset of models for sorting and evaluate the rest. We measure the accuracy of our predictions for new models using both instance-level and dataset-level metrics. At the instance level, we calculate the mean average error and the normalized agreement between our estimated predictions and the actual outcomes. At the dataset level, we assess the absolute difference between the estimated and actual accuracies, providing a global view of our prediction's accuracy without focusing on individual sample-level details. Section Summary. In this section, we efficiently insert new samples into our lifelong benchmark by estimating their difficulty compared to existing samples. To optimize this process, we rank models to subsample a subset for evaluation, similar to how we added new models previously. By recasting optimization objectives and using Algorithm 1, we sort models based on their accuracy, allowing for efficient evaluation of new samples and models within our framework. Section. In this set of experiments, we evaluate the predictive power of SNS for evaluating new models. Baseline equals char. Base. Shape equals circle. Fill equals softered. Draw equals white, thick. Drop shadow equals shadow x shift equals 0.2x. Shadow y shift equals minus 0.2x. Intercept equals 1 pt. Char. 2 winking face. When subjected to a varying number of sampling budgets, B group color, black, $and $E group I.E. We run our SNS framework over B group color, black, $13 E group different sampling budgets. 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,384, 32,768, on both lifelong ImageNet and lifelong CIFAR10. Unless otherwise specified, our main results in model eval, sample eval use the simple sorting by sum algorithm. Baseline equals char. Base. Shape equals circle. Fill equals Kleinblue 2. Draw equals white, thick. Drop shadow equals shadow x shift equals 0.2x. Shadow y shift equals minus 0.2x. Intercept equals 1 pt. Char. 1. Listing. 1. For obtaining B group color, black, $P. $E group and uniform sampling for the sample budget B group color, black, and $E group. We analyze and ablate the other design choices in design choices. We now present our main results. Key result 1. Extreme cost efficiency. From Fig. CIFAR 10 joint main. Fig. ImageNet joint main. We observe that our approach converges to a very high normalized agreement and low mean absolute error with 11,000 the number of evaluation samples, leading to extreme cost savings at inference time, from 180 GPU days to 5 GPU hours on a single A100-80 GB GPU. This consistently holds across both datasets on all three metrics: normalized agreement, mean absolute error, and absolute accuracy difference. Key result 2. Prediction error scales as a power law. We further analyze the observed B group color, black, $E_AGG, $E group against the sampling budget, B group color, black, and $E group. Relationship by fitting power laws in Fig. CIFAR 10 power law main. Fig. ImageNet power law main. The power laws take the form B group color, black, $E_AGG equals CN P $E group, where B group color, black, $C $E group is the scaling width and B group color, black, $P $E group is the exponential coefficient. We find that the power laws have large exponential coefficients. B group color, black, $P equals minus 0.18, $E group for lifelong CIFAR 10 and B group color, black, $P equals minus 0.23, $E group for lifelong ImageNet. This further demonstrates the surprisingly high sample efficiency obtained by sort and search, SNS. Key result 3. Highly accurate performance estimation. We note from Fig. Estimate GTACCS core joint main that SNS is able to very accurately predict the ground truth accuracies of models. At a sampling budget, B group color, black, and $E group, of just B group color, black, $512 $E group or B group color, black, $1,024 E-group samples. Our predicted accuracies almost exactly match the true accuracies, as measured by the Pearson correlations. B group color, black, $0.96 E group for lifelong CIFAR 10 and B group color, black, $0.97 E group for lifelong ImageNet at a sampling budget of B group color, black, $1,024 E group. Note that this performance prediction ability is especially surprising given these results are aggregated over 25,250 models for lifelong CIFAR 10 and 117 models for lifelong ImageNet, spanning a wide range of architectures, model sizes, and accuracies. Additional plots across a more finer variation of B group color, black, and $E group are provided in the appendix. In this section, we delve into experiments designed to test the effectiveness of our sort and search (S&S) method in evaluating new models. We conducted these experiments across a range of sampling budgets, specifically 13 different budgets: 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,384, and 32,768 samples. We applied these budgets to two datasets, lifelong ImageNet and lifelong CIFAR 10. Unless we mention otherwise, we primarily used a straightforward algorithm called sorting by sum for selecting the best predictions and uniform sampling to manage our sample budget. We also explored other design choices in a separate analysis. We now highlight our main findings from these experiments. First, we discovered that our approach is extremely cost-efficient. Specifically, we found that with just 11,000 evaluation samples, our method achieves a high level of agreement with the ground truth and a low mean absolute error. This efficiency translates into significant cost savings during inference, reducing the computational demand from 180 GPU days to merely 5 GPU hours on a single A100-80 GB GPU. This impressive reduction in computational cost was consistent across both datasets and all three metrics we considered: normalized agreement, mean absolute error, and absolute accuracy difference. Second, we observed that the prediction error follows a power law relationship with the sampling budget. By fitting power laws to our data, we found that the error decreases at a rate described by a power law with large negative exponents, specifically -0.18 for lifelong CIFAR 10 and -0.23 for lifelong ImageNet. This indicates a surprisingly high sample efficiency for our S&S method. Third, our method demonstrated a high accuracy in performance estimation. With a sampling budget of either 512 or 1024 samples, our predicted accuracies closely matched the true accuracies of the models. This was evidenced by Pearson correlation coefficients of 0.96 for lifelong CIFAR 10 and 0.97 for lifelong ImageNet at a sampling budget of 1024 samples. Remarkably, these results were consistent across a wide variety of models, encompassing different architectures, sizes, and accuracies, and were aggregated over 25,250 models for lifelong CIFAR 10 and 117 models for lifelong ImageNet. Additionally, we explored the task of estimating the difficulty of new samples by determining which models should evaluate these samples to accurately gauge their difficulty. We tested two methods, sorting by sum and sorting by confidence sum, across various model budgets. Our findings on the lifelong CIFAR 10 benchmark showed that both methods quickly converged to a low mean absolute error, with sorting by sum achieving this with just 64 models out of a possible 31,250. This represents a computational saving of 10,000 times, showcasing our method's efficiency in determining sample difficulty and facilitating their efficient integration back into the lifelong benchmark pool. Section Summary. In this section, we evaluate the performance of our sort and search framework on different sampling budgets for model evaluation. Our results show extreme cost efficiency, with significant savings in GPU days and accurate prediction of model accuracies even with a small number of samples. Additionally, we demonstrate the scalability of prediction errors with a power law relationship, highlighting the high sample efficiency achieved by sort and search. Section: Breaking down sort and search. In this section, we delve into the various design choices within our sort and search (S&S) framework and evaluate their impact on efficiency gains. We start by exploring how the number of models used for initial ranking affects performance prediction on lifelong ImageNet. We find that having more models at our disposal significantly enhances prediction accuracy. Specifically, when we use only 10 models for ranking, the performance difference at convergence is about 4% lower than when we use 100 models. However, it's interesting to note that the number of models doesn't influence how quickly we reach convergence. All methods tend to converge at the same rate, given the same sampling budget, but the accuracy of the predictions varies. Next, we compare 3 different sorting algorithms on lifelong ImageNet: sorting by sum, sorting by confidence sum, and sorting by recursive sum. Our observations indicate that using continual relaxation of accuracy prediction values as confidence values doesn't necessarily improve, and in fact, can decrease the predictive accuracy of our method. On the other hand, employing a multi-step recursive correction of rankings significantly enhances performance, offering a 2% boost in normalized agreement for all sampling budgets larger than 1024. This improvement is attributed to its ability to correct local ranking errors, which the global sum method fails to address. When it comes to sampling methods, we compare uniform and random sampling. Both approaches reach their optimal values quickly and at similar budgets, but begin to plateau after a certain point. Notably, uniform sampling outperforms random sampling, especially when the sampling budget is small, showing a 10% better absolute normalized agreement at a budget of 8. This advantage is likely due to uniform sampling's diversity-seeking behavior, which ensures a more representative coverage of samples across all difficulty ranges, unlike random sampling, which might miss out on certain segments. We also discuss how the errors in sort and search can be intuitively broken down. The total mean absolute error can be split into 2 parts: one that cannot be reduced by further sampling, known as the aleatoric sampling error, and another that can be minimized by increasing the sample size, referred to as the epistemic sampling error. The aleatoric sampling error arises from the inherent uncertainty in the data and the sorting operation, which cannot be eliminated by simply increasing the number of samples. On the other hand, the epistemic sampling error represents the gap between the optimal ranking prediction and the current prediction with the given sample size, which can be narrowed down by querying a larger fraction of samples. In our results, we analyze the effectiveness of sampling in lifelong CIFAR10 and lifelong ImageNet by looking at both types of errors. We observe that the epistemic error is quite low and converges to 0 quickly, meaning we can achieve the best possible performance with just 100 to 1000 samples on both datasets. The remaining error, which is primarily due to generalization gaps, cannot be further reduced. Additionally, we note that the recursive sum algorithm does not help in reducing this gap, as it is mainly due to new models not adhering to a single ranking order across all samples. Section Summary. In this section, we analyze the design choices in our sort and search framework, focusing on the impact of the number of models used for ranking and the different sorting methods employed. We find that having access to more models improves prediction accuracy, and using multi-step recursive correction in sorting provides significant boosts in performance. Additionally, we compare sampling methods and decompose the errors of sort and search into aleatoric sampling error and epistemic sampling error, highlighting the importance of diverse sampling strategies in improving prediction accuracy. Section: Open Problems. In this section, we delve into some intriguing challenges that have emerged from our work, which has shown great promise in making the process of evaluating lifelong benchmarks more efficient. Our exploration with the S&S method has opened up several areas for further investigation. Firstly, our current methodology is limited to a one-step process for sample ranking and model evaluation. However, for an ideal lifelong evaluation, it would be beneficial to optimize these steps simultaneously. This raises the question: how can we expand our framework to allow for multi-step continual ranking and evaluation? Secondly, we found that the precision of ranking can significantly impact the performance of new model predictions. Our error decomposition analysis strongly suggests that the way samples are ordered when evaluating new models can be a major bottleneck. Moving beyond a single sample ordering to more complex structures, such as having different clusters of models each with their unique orderings, or even implementing rejection frameworks for models that don't fit the established ordering, could significantly enhance our framework. Lastly, the identification of difficult samples presents another challenge. Pinpointing and labeling these challenging examples is crucial for lifelong benchmarks, yet it was not the main focus of our study. Exploring methods for selecting hard or adversarial samples within the context of lifelong benchmarking is a promising avenue for future research. To support this, we have compiled an extensive survey of related methodologies in the appendix. These open problems highlight the potential for further advancements in our understanding and capabilities in lifelong learning benchmarks, pointing the way toward more sophisticated and effective evaluation frameworks.